Today's lesson is on Chapter 1, Section 4, which is perimeter and area in a coordinate plane. And we're also going to talk about classifying polygons. So the definition of a polygon, it means, by definition, it means many angles. But basically, a polygon is a closed plane figure formed by coplanar segments called sides, okay? So there's three things that have to happen here. Number one, each side must intersect exactly two sides, one at each endpoint. No two sides with a common endpoint are collinear, and each endpoint of a side is a vertex of the polygon. And so let me just draw one and kind of go through these different explanations. So let's just draw a rectangle. And if you notice, a rectangle is sort of drawn here using four line segments. So the first thing says a closed plane figure. That means a closed two-dimensional figure. Closed meaning there's no open ends to it. Everything ends at another point, okay? It says coplanar segments. So here we have, let's say, A, B, C, and D. And what that means is that we know that AB, segment AB, is on the same plane as BC, it's on the same plane as CD, and the same plane as AD. Then number one, each side must intersect exactly two sides. So think about that. Let's think about side AD here. Notice that AD, right, touches AB, this side over here, and CD. So you're basically going to have, each end of segment AD. These are like the end points of AD, and of course there's going to be other sides that connect to those endpoints. Number two, no two sides with a common endpoint are collinear. So if you have, let's say, the common endpoint A, notice that AB and AD are not collinear. They're on different lines or line segments. And then the third one says each endpoint of a side is a vertex of the polygon. And again, notice that everywhere where they touch these corners, these are all called vertexes or vertices. Okay, so we'll get into more details about all this later, but just again, learning the definitions of the words. So again here, let's say, identify the figures that are not polygons. Okay, so let's just go through and say what are polygons, right? A is definitely a polygon. And the reason we know it's a polygon, notice that every vertex, we've got all our vertex here. Everything touches at the vertex, it's two-dimensional, everything is on the same plane. You have no open ends. So this is definitely a polygon. B is not a polygon. And it looks like it is, except for the fact that it's missing here. It's open. And we know that a polygon has to be closed. Okay? When we get here to D, I'm going to go to D. D is definitely a polygon. Okay, I'm going to skip C. We'll talk about C after. Notice again all the endpoints. Every endpoint has two lines that attach to it, right? We've got all these different points, and it's a closed figure, and everything connects, and that makes sense, okay? And then our last one is E, and again, notice we have one vertices here. This has nothing. This is an open shape. This is just definitely not. So this is not a polygon. So the only one that we start to question that I think is a little bit more complex is C. And we start to wonder, is C a polygon? And what happens here is, even though C and D look very similar, the fact that these lines crisscross here in all these places, that's what's going to make it not a polygon. Because remember, we talk about each point, right, has two lines that meet at that point. So notice we've got this line and we've got this line. But in this particular problem, we also have this one and this one. So we've got four lines meeting at the same endpoint. We also see that one of the restrictions was that the points that had the same endpoint, or the lines that had the same endpoint, could not be collinear. Well, if I draw a line this way, this would be part of the same line. And so again, this just doesn't meet the criteria for a polygon. So this would be not a polygon, okay? Now, once we know that something is a polygon and all of these three shapes are polygons, We can differentiate between a convex polygon and a concave polygon, okay? A convex polygon is a polygon where none of the lines that make up the sides, okay, have any points that are on the interior of the polygon. So we consider the interior of a polygon the inside of it. So all this open space here, we consider this the interior. So if I can kind of go to my lines and I can draw my lines out, my segments that make up my polygon, if none of those segments go into the interior, then it's convex. So this is convex, this one's convex, the second one, and the third one, notice again, I do my lines, and again, this is a convex polygon. A concave polygon, what happens here is that when I draw my lines, like we talked about, when I do my lines and I kind of go like this, if at any point my line crosses into the interior, which this one does, it's a concave polygon, okay? Again, notice that when I do this line, it goes into the interior, and so this is another concave polygon. So we just want to be able to differentiate between the two. Now, when we go to classifying polygons, what we try to do is we classify them based on their number of sides. And so if we have a three-sided polygon, we call that a triangle, okay? Tri meaning three, okay? So three angles or triangles, whatever. A four-sided figure, we call it a quadrilateral. And if you guys are familiar with quad core for a computer memory thing, I think in a processor, we might have your quadriceps, you know, in your muscles. Your quadriceps is really made up of four muscles. A person who is a quadriplegic has lost the ability to use their four extremities, okay? Their arms and their legs. And so again, we use quad in a lot of things, and so quad means four, okay? A pentagon, penta means five, so a five-sided shape is called a pentagon, okay? A hexagon, well, hexa, you've guessed it, it means six. Hepta means seven, so it's a heptagon. Another word for a heptagon, sometimes you'll see a septagon. So you might, depends on, you know, we'll say heptagon, but you will sometimes see septagon, and it also means seven. Octa, well, oct means eight. Think of an octopus, right? Nonagon means nine. So nine-sided shape. A deca, think of a decade or a decade of the rosary. And lastly, we have our 12-sided figure, which we call it a dodecagon, okay? 12 sides. Beyond that, okay, beyond the 3 through 10 and then the 12, we really don't go into names of everything else. At that point, we just call it an n-gon. And by that, we mean if the number of sides is 13, we call it a 13-gon. If the number of sides is 22, we call it a 22-gon, okay? And those shapes do exist, but that's just, we don't memorize the names of that after 12. So again, when you come over here to your problems, it says tell whether the shape is a polygon and whether it is convex or concave. And so here, when I look at this shape, if I was just talking about the outer edges, this would definitely be a polygon. However, this line here in the middle throws it off. Notice you've got three lines that reach this point, and you can't have it. You can only have two lines reaching a vertex or an endpoint. And so this is not a polygon, and therefore I don't have to classify it as to convex or concave. This one here, here's my endpoints, all my lines, you know, each endpoint or vertices only has two lines, two nonlinear lines attaching to it, or non-collinear. So this is definitely a polygon, and this is definitely a convex polygon, because when I do my lines, none of them go into the interior. This shape here, this is very hard to see, but this is actually a curved surface here. And so I know that this is not a polygon. A polygon has to have line segments as its side, and this is not a line segment, okay? And then my last one, I have this cross-looking shape here. And I know that it's definitely a polygon. It's a closed shape. Now, is it convex or concave? Well, again, I kind of got to follow my lines, right? Notice I draw that line and it goes into the interior. So I know this is a concave polygon. Now in example 2, we're going to talk about how do you classify the polygon by its number of sides. And then again, it's telling us whether the polygon is concave or convex, or we have to tell it. So again, in the first one, I noticed that I've got 6 sides to this shape, right? So there's 6 sides. And so I know that that is a hexagon, okay? So it's a hexagon. Now I have to determine, is it convex or concave? And again, notice when I kind of extend my lines, none of them go into the interior. So this is a convex hexagon. Okay, so if I was really going to write it, I'd kind of write it like this, a convex hexagon. When we go to B, this is a 4-sided shape. It is a closed shape. So this is definitely a polygon. It is a quadrilateral because it has 4 sides. And again, when I do my like extending, I see that nothing goes into the interior. And so I know that this is going to be a convex quadrilateral, okay? And when I go to C, I know that it's a polygon. Now the number of sides, sometimes it's hard to see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So this has 12 sides. So I know this is a dodecagon, again, because I've memorized that. And I know that when I do my lines, I'm going to end up in the interior. And so I know that this is a concave dodecagon, okay? Now, one extra thing that I want to talk about, I know it hasn't been mentioned here, it's not on this slide, but one thing is the topic of a regular polygon. If you come across a polygon that is considered regular, it means that all the sides are congruent or equal, okay? And all the angles that are formed are also equal or congruent, okay? So for example, if I look at A, right? If I go back here and look at A, I notice here that I have 6 sides. And if you notice on those 6 sides, they used a single tick mark for every single one. That means that tick mark is a congruent mark. That means that this side is equal to this one, equal to this one, equal to this one, equal to this one, equal to this one. All 6 sides are congruent. And then if you look at the arcs that form the angle measures here, notice that all these arcs are single arc marks. It means that every one of these 6 angles is equal as well. So this is not only just a convex hexagon, it is a regular convex hexagon, meaning that it is regular, all its sides and all its angles are equal to each other. And we're going to do a lot moving forward with regular shapes. When I go to B and I try to do the same thing and I say, well, is B regular or not? I'm going to look at it and I see that I've got this side here, the left side here has 1 tick mark, as does the right. Those 2 are equal to each other. However, this has 2 tick marks, which means it's not the same length as the ones with the 1. So I don't have 4 equal sides here. And if you look at my angles, I don't have 4 equal angles as well. These opposite angles here are equal and congruent to each other. These double angles are equal. The double tick marks are equal to each other. However, they're not equal to the other ones, okay? So this is not a regular polygon, okay? And in the third one, again, I would go through and try to determine if this would be regular or not. And when I look here, I see that not all the angles formed are regular because the angles are inside. So while this is 90 degrees and this is 90, this angle here is not 90. It's actually 270 degrees. So my interior angles are not all equal. And therefore, this one would be not a regular polygon either. So again, the whole regular thing might not come up here, but it's going to come up soon. So I wanted to make sure I introduced it to you. Now that we know what a polygon is, right? Any polygon that we can draw, that polygon is going to have an area and a perimeter associated with it. And so like any shape, now we have found obviously shapes of some basic, or areas and perimeter of some basic shapes in the past. You've done in middle school and elementary, probably maybe middle school, you've done the perimeter of, for example, a triangle, a square, and a rectangle. These are shapes I know that you probably covered when you were in middle school. The perimeter of a triangle, well, the perimeter of anything is the distance around the shape. So it's basically how long are all the borders of the shape. In other words, if I was to add side A, side B, and side C together, that would give me the perimeter of the triangle, okay? Same thing if I'm doing the square. The perimeter is the sum of all four sides. Now a square just happens to have 4 equal sides. So we could, for the square, the perimeter is either S plus S plus S plus S, or I could just do 4 times S. And then again here for my rectangle, my lengths, I've got 2 sides that are the length, 2 sides that are the width, and I know that my perimeter is either L plus W plus W if I want to expand it out, or I can use the formula twice L plus twice W, and that gives me the distance around the shape. So the blue that I'm drawing represents the perimeter, okay? Now, the area is the shaded part inside of the shape. It's how much area does that have, right? And so again, our formula for that is a little different. The area of a triangle is half base times height. The area of a square is side times side, or side squared. And the area of a rectangle is length times width. And so that's the area formula. So how does this pertain to what we've been learning? Well, remember that we might have shapes on a coordinate plane. And if I ask you for the perimeter of a triangle, you're going to need to know, you might be given these points here as ordered pairs. And I may say to you, what's the perimeter of the shape that those ordered pairs, that those vertices make? Well, you'll have to use your distance formula to figure out, well, how long is B? How long is A? And how long is C? And then add them all together. So we're going to take these old formulas that we know, and we're going to incorporate them now with some formulas that we've learned using coordinate planes. So let's start with example 3. It says, find the perimeter of triangle ABC. So they tell me that point A is at -2, 3. So point A is here. They tell me that point B is at 3, -3. So here's 3, here's -3. So point B is down here, right? 3, -3. Point A is -2, 3. And point C is -2, -3 here. Point C, -2, -3. And so I'm going to connect these dots, and I'm going to create the triangle that they're talking about. There. So I have this triangle now. Well, if I want the perimeter of this triangle, notice that I'm going to have to find AC, segment AC, this one, right? Plus segment BC, which is this one, plus segment AB. And that's going to equal my perimeter. So how do I do that? Well, I got really lucky with these horizontal ones, right? The horizontal line and the vertical line. In other words, AC is a vertical line. So it's very easy to identify the length here. I can either subtract my x's, because it's vertical, I only have to work with the y's. 3 minus -3 is 6, and the absolute value of 6 is 6. So I know that this here is 6 units long. I could count that as well, okay? When I get to BC, again, I know that this is 5 units long. Mathematically, I could use the absolute value formula and do -2 minus 3. The absolute value of -5 is 5. And so I know that this is 5. The tricky one comes with this diagonal line, right? I need to know the distance between point A and point B here. Now, we learned the distance formula yesterday. We know that AB equals the square root, and it's the difference of my x's, so I'll do top x and bottom x, right? I'll go top down like that. So I'll do -2 minus 3 squared, and then top y minus bottom y, 3 minus -3 squared. So come over to here, -5 squared, 6 squared. I get 25 plus 36, and that's going to give me the square, well, let me do over here. That's going to give me the square root of 61. So I know that the length of AB is the square root of 61. So if I was just doing the math and combining my like terms, I know that my perimeter is going to be 11 plus the square root of 61. If I want a more exact answer, I will have to go to my calculator and I'll have to figure out what the square root of 61 is. And the square root of 61 is approximately 7.81 units. And so the perimeter here is going to be 18.8, let's just say. Okay, so it's about 18.8 units. I'll let you know if I want the answer in just simplest radical form or if I want it actual decimals or whatever. And then we'll do our last problem. So our last problem here says find the area of triangle DEF with the following vertices. So we have to be very careful here and graph correctly, right? So D is 1, 3. So that would be here. We've got E is 4, -3. So it's here, right? So E is 4, -3. And we have F, which is -4, -3 here. And we try to be nice at first and give you some diagonals or some, not diagonals, but some vertical or some horizontal lines. So this one has one line that at least we don't have to work too hard on, right? Because like here's our triangle. Remember that the area of a triangle is always a half times the base times the height. Well, in this triangle, our base is right here. Our base is EF, okay? So what is the length of EF? Well, I can count, right? 1, 2, 3, 4, 5, 6, 7, 8. So I know that my base is 8. And my height is going to be a line that goes to the top vertices, and it is perpendicular to the base. So this line here is going to represent the height of my graph, and so of my triangle. So the length of this height is 1, 2, 3, 4, 5, 6. So my height is 6 units. So I know the area of this shape is half of 48, which is 24. So 24 units squared is my area. And so again, we have to mathematically kind of calculate this stuff. This base here, I found the base by counting. I could have, I know it's a horizontal line, so the only thing that changed is my x's. So I know the answer would be the absolute value of, my x's. So -4, -4, and that's going to be the absolute value of -8 or 8. So that's how I could have found it mathematically if I didn't want to count. And if I wanted to find this height the same way, I could have figured out that this was, 1, -3, and I could have found the height that way. But again, when you can count, count.